Okay, we are in the 4.2 notes. We are talking about this sigma notation, which just means sum. And we're about to tackle these kind of like shortcut formulas, but we will use these later on when we actually start doing like calculus problems. So, okay, I was talking about the first couple last time, how if we have like some constant times a sum, that's kind of like the same as like factoring that constant out and just timesing it by the entire sum. And if we have two separate like rules that you're summing, we can like split up the sigma notation because you can like add those terms in any order. So if this rule was like, oh, I'm adding the first 20 odd integers, and then I'm adding, I don't know, n factorial something, you could find the sum separately and add them together, and that would be the same thing as this notation right here. Okay, so these ones, I'm going to show you just kind of like why these like work, but you don't really need to like explain that. This class isn't really focused on the summation notation piece of it. We're just going to connect it to calculus in a little bit here. But I'm just going to quick show you just like a little example of each to show you like why these like formulas kind of work. Okay, so you can write them down if you want to. You don't have to though. So this first shortcut, if we have the sum of, let's say, the first 3 terms, and my rule is a constant, let's say my rule is 7. So what that means is you're plugging in 1 into your rule, but you're like, what the heck, there's no place to like plug in 1. So my output's always just 7. Okay, it's kind of like a horizontal line. When you have like y equals 2 is your rule, and there's like no numbers to plug in, you're just going to get that constant output of 2. That's kind of my rule here. I'm going to get 7. And I'm going to stop after I do 3 terms, because that's technically plugging in 3 for I, not that this number tells me it's to stop there. So we would get 21. Okay, now to show you this shortcut, they said it's the same as taking that constant number, which in this case is 7, times however n many number of terms you're doing, which you'll see those you get the same thing. Okay, so in red right there, maybe I could keep this whole thing red. In red, there's kind of like the shortcut formula is like, hey, if we have a constant, you can just take that constant times however many terms we have. That makes sense because that's the same as adding 7 3 times, right? Either way, we get 21. Okay, so there's kind of why the first one works. If you have some constant, just times it by however many number of terms you have. My second shortcut here, if my rule is just the number itself, if it's just I, let's do like a really basic example. We did some of these yesterday. This is good review over the notation too. Let me actually give you a number here. Let's see. Let's say we have n is 4. Okay, so we know what this means. It means we're going to start by plugging in 1, and then we're going to keep going up until we plug in 4, and the sigma means we add these together. Okay, we get this sum to be 10. The shortcut, and the reason why there's shortcuts, now obviously that one was way easier to just write out, but if they wanted to find the summation when my number of terms was like 365, I don't know about you guys, but I don't want to do 1 plus 2 plus 3 plus 4 all the way up to 365. So in that case, we're going to use this like shortcut or this formula, probably a better way to say it. And I can take whatever my n is, which in this case it's 4, times that number plus 1, and divide it by 2, and we should still get the same sum here. So here I have 4 times 5, which is 20, divided by 2, I still get 10. Okay, so there's just like a little mini, not even really a proof, but why that shortcut works. So we're going to use that often because we're going to start doing like bigger sums, like bigger number of terms. Okay, the third one, I'll show you this one quick. Oh, I was doing all my shortcuts in red. Let me be consistent. Okay. The third one, back to blue here. Yes, thank you. 10. 10. They're both 10. All right, the third one. For this example, I just did, we're going up to I equals 3 for I squared. So my rule is we're squaring the number. So obviously I'd start by plugging in 1. And notice how like you have to start at 1 in order for these shortcuts to work. So here we're starting at 1, and then I go 2, and I'd stop when I get to 3. The sigma tells me to sum these all. So we have 1 plus 4 plus 9, I get 14. Okay, obviously that one's not too bad because I'm only finding 3 terms. Or I could use this formula here. And again, you don't have to like really, I know it sounds silly, but you don't have to really understand where these formulas come from. We're just going to use them. All right, we could also do my n, which in this case is 3, times that number plus 1, times 2 times that number plus 1, and divided by 6, and that formula tells us we should also get 14, which if you multiply that top out and divide by 6, you do indeed get 14. Okay, one more, I'll just show you quick. 4. If my rule is i's being cubed. I think I did 3 for this one as well. Yeah, let's just say we have 3 terms here. We know we could find this by doing 1 cubed, plus 2 cubed, plus 3 cubed. That's what that summation says. So 1 plus 8 plus 27 give you 36. The shortcut formula says, hey, instead of doing that, you can just square n plus 1 squared, divide that by 4, and we should get the same thing. And here you would do 4 squared 16 times 9 divided by 4. We do indeed get 36. Okay. So there's just a little like example of why those shortcuts, if you will. Shortcuts or formulas, however you want to think of them. I guess formulas is probably a better way. Why those like work. And we're going to use them a lot. So I won't make you memorize them either. I'll give those to you on an assessment. If you ever need them, you don't need them a whole lot. Okay, so let's try a couple sums. But it says use the properties of summation. So we can use, these properties. If I maybe have a constant, I can kind of factor it out. Or if I have 2 separate terms, I can find the sum separately. And also any of the formulas to evaluate the sum. Use the summation capabilities of your graphing calculator to verify your result. Okay, so now these are getting more intense, and it's like, all right, now I need to, find, here's my rule, 4 times I. And again, we could, if we wanted to, do 4 times 1 plus 4 times 2 plus 4 times 3 plus 4 times 4, all the way up until 24, but that would take forever. So this is where these properties, or these like shortcuts and formulas, will kind of help us. So the first thing I see is I have 4 times I. So anytime you have a constant number, you can think of, okay, let's just kind of factor that out. Because if I do 4 times 1 plus 4 times 2 plus 4 times 3, and I showed you this yesterday, that'd be the same as taking 4 times 1 plus 2 plus 3 plus yada. So we can bring that 4 out kind of like in front of the sigma notation and write it like this. That's the same as taking 4 times that sum. And you're like, okay, well, this would be a little bit less work. I could probably write it out from here. I could do 1 plus 2 plus 3 plus 4 plus 5 plus all the way up to 24. But again, we don't have to. We have that little shortcut or that formula for I. This is like that second one there. So we can find this sum by simply doing the sum right here. N, which is 24, times 24 plus 1 times n plus 1, all divided by 2. Okay, I just got that formula from that second one. And then, of course, I got to times this by 4. Okay, you guys quickly figure out what that is. I'm going to pull up the graphing calculator and remind you of how to use the sum button. Do you get a number?
1200.
1200. That's what I got too. 1200. Okay, let's check if that's right on our graphers. So, as a refresher, to get to this button, you hit alpha, F2, so alpha window, and this list should pop up. Look, derivative is on there. Ooh, look. Pretty soon I'll be able to use that. Stay tuned. Summation is option 2, and then we just use x for our variables. So this one would be from x equals 1 for 24, and my rule is 4 times x. Nice work. You guys did it. Okay, these are kind of fun. Let's try another one. Here I have I minus 1 squared. So I would multiply this out because we have a rule for I squared and we have a rule for I. So I'm like, okay, if I could kind of write that in its multiplied out form, that might kind of help me see some formulas I can use. Okay, so if I were to multiply that out, I get I squared minus 2I plus 1. Probably put that kind of like in parentheses because you're finding the sum of all of that. Okay, here's where this property comes into play, of where you can almost think of this as you have like 3 separate rules. You have I squared, you have 2I, well, times negative 2I would be the better way to say it, and then you have this plus 1. And since we can add in any order, we could split this up and find the sum of the first rule, which is I squared. We could subtract the sum of this rule, and at the same time, I'm going to bring that 2 out in front. So like this, 2I, and if you need to do that in 2 steps, that's fine. But for those 20 terms, okay, follow my thinking here, and then I can add the sum of 1, which that's just like that constant rule. So we'll apply that in a second here. Okay, so I kind of used 2 properties in one there. I broke up the terms because you can add in any order. And then I can see this more clearly, like, oh, here I can use my shortcut for I squared. Here I can use my shortcut for I. Okay. So my shortcut for I squared, I'm looking at number 3 on that summation formula list. I would do n, which in this case is 20, times 20 plus 1. And folks, if you don't want to like write it out like this, if you're like eccentric, I can do 20 plus 1 and just write that as 21. That's totally fine. I'm just doing this for sake of showing you, plugging it in the formulas is how I'm getting all these numbers. Times 2 plus 20 plus 1 all over 6. Okay, there's that first shortcut to find that sum. Because again, I don't want to do 1 squared plus 2 squared plus 3 squared all the way up to 20. That will give me the sum in one step. All right. Now I'm going to subtract, because this is a negative 2I, 2 times this sum. All right, so this one was like the one we just did. Number 2 in my list there, where I take n, which is 20, times n plus 1, which is 21, all over 2. Okay, now careful here. Sometimes people just think, oh, I'm just going to add 1. My rule is 1, and how many times am I adding 1? 20 times. So that's really got to add 20. Okay, and that is that constant rule. So another way you could write that out using the rule is I got to take this constant number 1 times n. That's technically rule number 1 on my list. Okay, I just wrote down the final answer. I mean, in my calculator, I would probably do it like in 3 steps. We can do this one together in the calculator. So I would probably do like 20 times, and I just do 21 times 2 times 20 plus 1. Find that, divide that all by 6. Okay, there's my first piece, 2,870 plus 1. And then I'd probably do the next one. Obviously, those 2 cancel out, so that's just 20 times 21. Okay, that I could probably do in my head, 420. Minus 420, that's this one. Plus 20. Okay, this is what I got. 2,470. Oh yeah, duh. You could do minus 420 plus 20 is minus 400 minus 400 from that. Okay, that's probably how I type in my calculator. Let's check it quick with the summation tool. Alpha, window, summation, x equals 1. We're going up until 20. And my original rule in parentheses was x minus 1 squared. Ooh, yeah. Okay. We're just going to do one more for funsies. That'll move on. Then we'll start. Oh, yeah. Okay. It's pretty soon we're going to start connecting it to calculus. We have to understand this notation first. Okie doke. So again, I see this. I'd start by multiplying it out. So I'm just going to quick do that like right underneath here. I have I times I plus 3 squared would be I squared plus 6I plus 9. So that'd give me I cubed plus 6I squared plus 9I. Once I multiply that all out. So that's the same as finding this sum. Now, very similar to the last one, we can break this up. With finding the sum of my first rule, which is I cubed. You have a formula for that. Second rule, 6 times I squared. Bring the 6 out in front. We have a shortcut. Oops, where did I get the 4? It's supposed to be the 7. Shortcut for I squared. Plus 9 times I, so I'm going to bring that 9 in front. Times the sum, so I have a shortcut for I. You guys getting pretty good at drawing those sigmas? Okay, dude. So, okay, so I cubed, that's that fourth formula in your chart. That is n squared, 7 squared, times n plus 1 squared, so times 7 plus 1 squared, or you could just write that as 8 squared, all over 4. Again, don't you worry your pretty little heads about where that comes from. Somebody discovered it for you. It's just a formula you get to use. Plus 6 times, okay, my 1 for I squared. This one's the long one. N, 7 times n plus 1, so times 8, times 2, times 7 plus 1, so times 15. And that's all over 6. Plus 9 times my summation formula for I is n times n plus 1 all over 2. Okay, I'm just going to give you a final answer. I feel like we've done enough of these. I got 1,876. That seems kind of low. I guess we are only doing 7, up to 7, so. Mark's checking it for me. Pressure. We good? Okay. Any questions with that? Starting to get a little more comfortable with the notation? Good, because now we're going to throw calculus into it. Okay, this is where, oh, this is so exciting. Okay, let's just do it. Let's just get after it. All right, so it says, use the summation formula to rewrite the expression without the summation notation, so without sigma, aka we're going to use our shortcut formulas. Use the results to find the sums for when n is 10, 100, 1,000, and 10,000. Okay, so here we talked about this when we were writing out sums. Like so, and I mentioned that this 1 over n is like really just like a constant, because if you could check down here, the number we're plugging in for was k. That was part of my rule. So this 1 over n was really just like a constant. So if you look at this summation notation, my rule is I'm going to take I plus 1 and divide it by n squared. And then we're going to go through and do this for, okay, what if n is 10? What if n is 100, 1,000? So this n is like a constant number, okay? And this I plus 1, that's kind of like my rule, because that's the number that I'm plugging my my numbers in for, my values in for. Okay, so that 1 over n squared, I'm going to kind of like factor in front that constant, because we know if we have some constant times a sum. So this is really like, you could picture this as you have 1 over n squared times I plus 1, right? So I'm going to kind of bring out that constant. And this would be the same as timesing the sum of I plus 1 by that constant. Okay. Then I see I have I don't want to say sum because I don't want to confuse you with summation. I see I have that addition sign, so I can break that up. Okay, so I'm going to break this up as that. And then I just wrap parentheses around this because this whole thing is being times by that constant. And then we can use our formulas or our shortcuts to find these sums. Okay. So we have this 1 over n squared is being times by all of this. So my shortcut for I is n, and obviously this is for any number, so n times n plus 1 over 2. That's my shortcut for that one. Plus, here my constant is I just take this number 1 times however many times I'm adding it together, so n. Okay, let's clean this up a little bit. So I have 1 over n squared times, here, I'll distribute this, n squared plus n over 2. This is obviously just n. I'm going to make common denominators here so I can add these together. So here I'm going to times this top and bottom by 2, so I get 2n over 2. Just trying to simplify this a bit. Then I can add those together. So I get n squared plus 3n over 2. Then I can multiply those fractions together. Multiply the tops, multiply the bottoms. I get here, which they all have a common factor of n, so I could simplify to here. Okay, so that is my way of rewriting this sum without the sigma notation. That sum is the same as taking n plus 3 divided by 2n, using all my formulas and shortcuts for any number that we want to stop at. That's what that's saying. So then from here, I don't know about you guys, but I think that would be a lot easier to just plug in my numbers, my different values into this versus doing like the summation every single time and breaking up the same rule every single time. So from here, we're going to make a table, and we can use our graphing calculator for this too. All right. So my table, I'm going to do my different values for n. And then here's my rule. I'm going to take that number plus 3 divided by 2n, and that will give me the sum. Okay, so we're going to do this for 10, 100, 1,000, and 10,000. We're going to see what happens here. So in my graphing calculator, I'm going to plug this in for y1. And then just use my ask button and test out these different n values. Okay, so obviously I have to use my x button. Divided by 2x. Okay. So if you hit table setting, which is second window, make sure your independent is on ask. And then you can go to your table. And we're going to do for 10, 100, 1,000, 10,000. Okay. So you get 0.65, 0.515, 0.5015, 0.50015. Let's write those down. Okay. So you're looking here and you're like, you think as like my number of terms, since we're starting at 1, I can phrase it that way. As my number of terms is going up, my sum would get really, really, really large, right? But it kind of depends on what the rule is. We have this, yes, we're plugging in a different number into like that original rule, plus 1 every time, but we're dividing it by this constant n squared. So as that number gets bigger, now you're dividing it by a bigger and bigger and bigger number. Okay, so that's why it seems to almost level off. Do you guys think this is like approaching some value as these are getting bigger and bigger and bigger? Yes.
Almost directly half.
Yes. So we ask yourself, is this approaching? Is it approaching half? What calculus tool allows us to find if a value is approaching or limiting towards a number?
Limit.
A limit! All right, so let's try this. If I take the limit of this rule as n gets bigger and bigger and bigger, so we'd say as n approaches what? Infinity. Okay, do you guys remember how to evaluate limits at infinity? And this works for positive or negative infinity. There's like a little strategy.
If you're like dividing by the number, then it's zero.
Yes, that's going to come into play. There's like an algebraic strategy we do to like simplify this a little bit. Remember?
Is it like the left and right?
You're thinking asymptotes, which we would have to do, but we don't need to in this case. But for horizontal asymptotes, we do look at the as it's approaching positive and negative infinity. Divide by the largest power in the denominator. Yeah, remember that? So if I look at my denominator here, my largest power of n is n. I'm going to divide everything by n, and the way we write that is like this. Times everything by 1 over n. Oh my gosh, we're just constantly reviewing. All right, so that would become n over n. And then Delaney, what you said about as n gets really, really large, that's going to come into play next. 3 over n. And my denominator, 2n over n. Okay, so let's go ahead and plug in infinity. Obviously, that simplifies to 1. 3 over a really, really large number is going to go to 0. 2 over 2n over n is just 2. So, Dalton, you're right. It is going to approach a half. Okay. All of this is going to connect summations to calculus in a second. We're going to use limits. And we're going to use the summation notation to add up area in calculus. All right, so here's kind of like our second warm-up. That was all almost just like a little bit of like, hey, here's some algebra you need to know to do this lesson. So that was kind of like a little intro. I don't want to call it algebra, just like intro of like notation that you haven't seen before with like that sigma notation. Love this problem. This is really great segue into understanding the calculus side of it and how it's going to be used. So here's like your warm up to the actual calculus part. You're on the Polar Express, and it's moving at a steady rate of 75 miles per hour from 7 a.m. to 9 a.m. What was the total distance that you traveled on the Polar Express? I'll give you 1 minute to think about this and write down a number. Your steady rate. So maybe the train left at 6:55, but right at 7 a.m., it was going 75 miles per hour all the way until 9 a.m. So in those 2 hours, how far did you travel? Don't overthink it. Okay, anybody got a guess? Yes.
150 miles.
What's your guess?
75 miles.
What's your guess?
150.
Your guess? Jason.
150.
150. Because it's for 2 hours. So if we're going 75 miles per hour, 7 to 9 is how many hours?
Mark just wanted to be different.
I thought it was a trick question.
I know, that's why I was like,
know,
don't
when
overthink
you said
it.
75, I was like,
Wait,
am I not?
wait.
That's why I waited there.
I mean, I have 150 on my calculator, but I was like,
Seems too easy. I mean, what you guys really did there, remember this like little equation? You probably do it in like science and like we do it in like algebra and stuff. That distance is your rate times time. Okay. So right here, my rate is 75 miles per hour. times my time here, my time span of 2 hours. Well, let's throw a little unit analysis from like probably chemistry at you, right? Okay, we get 150 miles. Now I want you to write that out just for sake of seeing what you're doing here. You're taking 75 in your head. You took 75 times 2. Delaney, is that how you come up with that number in your head? 75 times 2. Beautiful. Okay, now let's make this connection to a graph. So the first thing I want you to do is draw me a velocity and time graph representing this train. So as your time increases, remember, velocity, speed, what would the velocity graph look like? How would you graph like its speed? Oh, that's beautiful. Yep. It's a constant speed, right? That's saying my speed is increasing over time. Constant speed of 75 miles per hour. So let's say my time here's 7 a.m. Here's 9 a.m. See if you can, we can kind of do this together, make a connection between this formula we used here and the graph. I forgot what this star says. Oh yeah, that tells me the answer. Any ideas of how we could somehow get 75 times 2 by looking at this graph? Sorry. I'm trying to get you guys to try it. Where does the 75 come from? What did you say? The rate. I thought you said the height for a second. The height or the rate. Okay. Remember what we did before? How we were always cutting boxes?
Just on the area of the square under area.
Exactly! If I were to make a little rectangle here, how do you find the area of a rectangle? Base times height. Base times height. My base is 2 hours. And my height was 75. And again, think of your units. Your time is in hours here. Your velocity, your speed is miles per hour. So we could get that same distance by doing 2 hours times 75 miles per hour, 150 miles by finding the area under the graph. So here's a connection. The distance traveled corresponds to the area of that shaded rectangle. Nice job, Mark. He discovered calculus. We'll add you to the list of fathers of calculus. I think there's 3 of them. Okay. So here's how we're going to connect. Oh, shoot, we only have 1 minute left. That's okay. This is a good spot to leave off. Basically, what we're going to do is we're going to use the sigma notation a little bit, but we're just going to basically sum up all of these areas of rectangles to estimate the area under a curve. I kind of just like gave it away, but that's all right. We'll stop there. That'll keep you interested over the weekend. That'll keep you wanting more calculus. Yeah.